session about approaches to mitigate the nutrient pollutants from water. And we have a wide range of new faculties discussing that. Now we have district with industries. So without further ado, we will get started with our session. And the first person in the panel to give us some idea about and adoption from concept to prototyping is Professor Tao from our own SUNY. So let's get started. Yeah.
Okay, my talk will not be pure technical. It's kind of combination of technical transfer and research. Echoes kind of this morning's plenary session. The technology I'm going to talk is, the principle is very simple. Whether that means apply vacuum to strip ammonia out of wastewater and absorb the ammonia gas into a solution as a value-added product. So principle is simple, but we had challenges when scaling up. So I want to share my experience with technology development from the proof of concept to prototyping. Whether can be applied to high ammonia wastewater such as anaerobic digestive sludge and animal manure. I use the municipal wastewater treatment as an example to justify the market fit of whether municipal wastewater has both ammonia, that's inorganic, and organic nitrogen. Organic nitrogen is converted to ammonia in the secondary biological treatment, and ammonia is then assimilated into microbial biomass, that's sludge. When the sludge is thickened and anaerobic digested, organic nitrogen in microbial biomass is further converted to ammonia. So after dewatering of the digested effluent, you dispose biosolids, get rid of organic nitrogen. And ammonia in the separated liquid that can be very high compared to influent, that's 20 milligram. But here, that's raised up to usually more than 800 milligram per liter. So this sludge side stream contribute nitrogen loading to the mainstream more than 50%. For wastewater treatment plants, they have two options to remove ammonia, but either in the mainstream for ammonia removal using nitrification, denitrification, or recover ammonia from the side stream. It's well conceived that it's much more cost-effective to recover ammonia from the digestate than ammonia removal in the mainstream, mainly because here you see the flow rate, that's just 1% of mainstream flow rate, but higher ammonia concentration. So that's favorable for ammonia recovery. The technology for ammonia recovery is largely in development. And VESA is one of the early innovations. Currently, there is one technology for ammonia recovery in full-scale application. That's gas stripping. For a stripping tower, which button? For a stripping tower, hot air or steam can be introduced from the bottom of the tower when water is distributed from the top. And the air bubbles carry ammonia gas out of water. That ammonia can be absorbed into sulfuric acid solution to recover ammonia. But it's not widely adopted, mainly several technical and economical drawbacks. And another technology that's Trivedi recovery that remove both ammonia and phosphate, but stoichiometrically, it mainly remove phosphorus, remove usually less than 20% ammonia from wastewater. So basically, it's not a technology for ammonia removal. So far, mainly that's about gas stripping. To strip ammonia out, we need first to convert aqueous ammonium to ammonia gas. So the ammonia gas can transfer from water to air bubbles and carried out. And this conversion is achieved at increased pH and increased temperature. Mostly for air stripping, increase water pH to above none. And if heated, for example, to 60 degrees Celsius, then the free ammonia gas account for more than 90% of total ammonia ready for ammonia stripping. So our first idea was to test the effect of temperature on ammonia removal. We didn't introduce any stripping agent, stripping gas, just heat the wastewater. We did differently is we tested temperature until boiling. So we used the dairy manure after digestion, and it boils at 102 degrees Celsius. And surprisingly, we found that if it's boiling, it's much more efficient to remove ammonium. Then if like here, this is 97 degrees, just 5 degrees lower, much slow ammonia removal. So that's surprising because we realized that different removal mechanisms, if not boiling, basically ammonia is removed by diffusion through the small liquid surface area. But if it's boiling, vapor bubbles form generally or naturally in water. So that means larger interface for ammonia transfer from water to air bubbles. So that's overall, that's more efficient. And if you heat water to boiling, that's energy intensive. So we want to reduce energy consumption. We introduce the vacuum. That means reduce the pressure from atmospheric pressure 101 kilopascal to lower pressure, that's vacuum. And at these combinations of temperature, you reduce pressure, you reduce the boiling temperature. And we found the optimum that's 65 degree at 25 kilopascal. So that means reduce the energy consumption. That's under boiling conditions, fast ammonia removal. We call that vacuum stripping. So we got a pattern for that vacuum process. So we got to scale up. And this shows our original lab setup, glassware setup. That's technology readiness level 3 and 4, just to prove the concept, the principles. To scale up, we first build a functional prototype. That means we have physical elements that can be operated under real conditions. And this is a stainless steel vessel. We have installed 2 electric heaters. And we can add 10 liters or up to 40 liters of wastewater to this stripper and heat it to 65 degree, 25 kilopascal. This is a demister similar as this glass condenser to retain moisture. And its separated ammonia gas is sucked to sulfuric acid solution. And we tested with different amounts of wastewater loaded in the stripper. And when we load more wastewater, feed depth increased in the stripper. And because you load more, supposed to recover more ammonia in terms of mass. But it increased initially, later on when depth larger than 20, no change. And stripping efficiency, we use ammonia mass transfer coefficient. It decreased with increasing feed depth. And KLA, it's proportional to stripping rate. So we found that for sludge digested, optimum feed depth, that's 20 centimeter. We also tested with dairy manure digested, optimum just 15 centimeter. That's too shallow for scale up. But we also continued to test with different type of wastewater to look at the optimum depth. We got good results, similar as the lab scale setup, and we recovered the ammonia sulfate, very high purity, greater than 98%, so we can sell that as a nitrogen fertilizer or reagent grade chemical. So for scale up, we can't just load 15 to 20 centimeter. Our solution was that for full-scale application, we can have tall stripper. We can mount vertically 9 tanks. Each tank can be fed to the optimum feed depth. But all the tanks share fewer strippers. 4 strippers can share one vacuum system, one absorption system. That's our vision for full-scale design. And before full-scale application, we need to demonstrate that. And we build a 3-pool system. This is stainless steel tank vessel. We mounted 3 tanks vertically. And vapor moves through demister and goes to absorption solution, and escaped moisture further retained in the cold trap. And we tested with sludge digested and landfill leached. Each batch, we loaded 88 liters of wastewater to each tank. So total capacity, that's 250 liters per batch. We got similar results as large as the single pool vessel system, efficient. And we collected ammonia sulfate crystals. Originally, it was cooled. The absorption column was cooled. So got chunks of ammonia sulfate in the column. And later on, we poured the solution to sieves, collect the crystals. The problem we found that we load 250 liters per batch, and 12 to 15% water lost as vapor. That means because vapor carries latent heat. If you lost more water as vapor, you lost latent heat. That means you need to reduce water vapor loss to reduce energy consumption for heating. So for that purpose, we added one condenser. We added one condenser on the corner. That's tuber shell condenser. Inserted that to the demister on the top. So more moisture can be retained, flush back, retain the latent heat. And the issue is because vapor from all the tanks meet in the stripper head and heat the stripper head to 78 degrees. And when vapor condenses, temperature decreased to 74 at the top of the demister. And we further tested with landfill with the condenser inserted in the demister. We found that we could retain 96% of the stripped ammonia in the absorption solution. Compared to previous, we can only retain 22% of ammonia in the absorption solution. And 78% moves back to the cold trap, dissolved in the condensate. So we reduce the water vapor loss, increased water reflux, and was able to recover almost all the stripped ammonia. And based on this sketch, that means if we install non-tanks in one stripper, the principle can change. So to facilitate the full-scale application, we simulated the process, hydrodynamic processes. The solid, this line shows the bubble pond. So for single pool vessel, the mist temperature reduced to 50. It boils at 65. At this temperature, ammonia fraction in condensed state, that's very small, about 5%. In the vapor, that's more than 58%. So that means efficient stripping and the separation of ammonia. But with the three-pool system, stripper head temperature increased to 78. Top of the demister just decreased to 74. And ammonia fraction in the condensate, it's a little lower, but the vapor ammonia fraction also lower. So we installed a condenser in the demister, increased this fraction just a little bit. So next stage, we are going to test, modify the demister, and ideally reduce the demister temperature to 65, and hope the vapor will have more ammonia to separate. So that's our next stage. It's more complicated to find the optimal condition for design, full-scale design. And I'll just quickly go over, because for commercialization, you always ask about the cost. This is our latest estimates of the costs. And we found that sulfuric acid, the largest part. Second, that's sodium hydroxide to adjust pH. Energy consumption actually is small if we use the heat exchanger to recycle the heating energy. And total operation cost, that's $1.5 per kilogram nitrogen recovered. And revenue from selling the ammonia sulfate, that's 2.46. So that means with the vessel, we can make profits, not just to reduce the operational cost for ammonia recovery. And further about benefits, we found several more benefits, especially when we couple vessel with anaerobic digestion, depends on where you put the vessel in the digestion system. And I don't have any technical conclusions. My conclusion from the technology transfer point of view, I would say that scaling up, it's not just upsizing. The design principle can change when you scale up. So you got to be patient, to be persistent. And you need fundings to support both fundamental research and applied research.
Oh, sorry. Whoa, okay. That makes a whole lot of difference. I hope it was okay. Oh, yeah, he can use this one, right?
Hello, everyone. My name is Jian Liu, or Ken from Rochester Institute of Technology. It's my pleasure to be here. I joined IIT a couple years ago. So this work about ammonia capture is majority done at Northwestern during my postdoc work. So today I'm going to talk about using zirconium-based metal organic framework to capture ammonia. So ammonia is has a very rich chemistry because the nitrogen and hydrogen, they can interact with water, with other metals. So I talk about the two types of reversible and irreversible uptake. So it's a majority about chemistry rather than engineering. So here is, as we know, ammonia is toxic. So it's one of the aerosol contribute to the environmental hazards. It's different from carbon dioxide. It will not make the global warming issue, but it will contaminate the environment, causing lots of environment and health issues. So removing trace amount of ammonia from the environment is kind of important. I read a literature talking about ammonia concentration in Finger Lake region. It's particular higher because of lots of this grape tree growing for the one in this region. And so ammonia at the same time is also a clean energy source because it has only nitrogen and hydrogen. So it's not contaminating the environment in like global warming way. So, but has very high density of hydrogen compared to methane, a little bit lower, but it's still a little high. Now, if we look at this, the graph, same amount of 10 kilogram of hydrogen stored in different kind of ammonia carrier or hydrogen carrier, liquid ammonia. Here is, I think, all right. Okay, so now you can see in the third, liquid ammonia has a very high density compared to either pressurized hydrogen gas on the right and also liquefied. So that means using same container, it can have higher density, thank you, to store this like hydrogen further used. And also it can liquefy it very easily, not very easily, but very better than hydrogen. You need 200 bar. Here is only like 2 bar, a little bit lower temperature. Now, it can directly or indirectly use in the fuel cell. So here is one example from, I think, Northwestern Professor Haley group. They did using ammonia directly go through this kind of membrane. And here has system modified ruthenium carbon nanotubes, and ammonia can decompose to get hydrogen. Hydrogen can use in these fuel cells. Now, here is one question or one problem is the trace amount of ammonia will decompose this membrane in the fuel cell. So remove this trace amount of ammonia or separate ammonia from nitrogen and hydrogen is pretty important. Okay. So here, as I talk about ammonia is, probably we know ammonia is a base. It's peroxide acidic base, it's a peroxide base and a Lewis base. So the base comes from the nitrogen, right? It has 2 lone pair electron, can donate electron, and can also accept protons. Now here, this electron can donate to the metal, and a separate proton can get ammonia ions. So here is this acid-base interaction is relatively strong because the chemical interaction happens. So it can be used for remove ammonia, trace amount ammonia, or separate ammonia from nitrogen in very low concentration. And here is at the same time, so it has hydrogen. So the hydrogen bonding can interact with ammonia and also interact with the surface of oxide to generate this physics option. So this can be used for storage. Now here, when we think about to increase this interaction between ammonia and the materials, we found out one material is called metal organic frameworks is very good for ammonia capture and also storage. Actually, people use a lot for gas storage using metal organic framework. Now, the reason is because it has it's a decent amount of Lewis and porosity acidity sites, either open metal sites or the proton exposed on the node, and also has broad pore size and pore volume. So for people who are not very familiar about MOF, MOF is made, it has two parts, inorganic parts and organic parts. The inorganic part has metal ions or clusters. So by changing different metal ions, you can get different kind of clusters or different coordination numbers and different coordination environments. And here, like a metal oxide, metal sulfur, or metal nitrogen bond. And here, organic linker, you can do different types of linkers, like a porphyrin, like a tetracarboxylic. And also, when they connect with each other and assemble periodically, you can get this structure. Now, here is some literature reported MOFs. You can see they have different kind of pore size, pore volume, and different topology can be used for separation and storage. Now, it's surprising. So this usually is a nanometer size, but it's tons of different pores accumulated can have very high surface area, usually like 1,000 square meter per gram. Now here we focus on one of the MOF called M1000. It's zirconia-based MOF. Why we study zirconia-based MOF, zirconia oxygen bond is pretty strong, so it can be used to do lots of work under harsh conditions. Now here the node is inorganic part is 6 zirconia connected by oxygen, and on each zirconia they also have these ligands hanging out to the pore. So here it has OH and water. Now look at this node. We thought this is all protons. So here is peroxide acid. So we think because ammonia is the base, so all these proton acid can interact with ammonia to do this work. That's the idea comes from. Now here, the parent linker is just connected with the node to get this periodic structure. Now here, this MOF has a very big pore. This is 3 nanometer pore, and this triangle is 1 nanometer pore. So the 3 nanometer pore, it has a very large pore volume, can store the ammonia. So it's interconnected by the window. It's about 1 nanometer size, so making sure the gas can transport without any diffusion issues. Now, if we look at this as I talk about, this zirconia node has about totally 16 peroxide acidic protons, including this OH, water, and this bridging OH. Now we did this basically 3 types. Now we did this titration, acid-base titration. We figure out they have different pH. So the higher pKa volume indicate it's like a lower acidity. Now you can see here, this is the highest acidity is this bridging OH. So now we think about they have different pH. We're curious about how these different protons contribute to ammonia capture. Are they just physics option or some chemistry option? So first, we blocked 2 types. So we only focus on this major, this bridging OH. This is the highest acidic proton. Now we got single crystal structure. We confirmed this structure. And we did this called FTR or in situ FTR, reflectance FTR. Usually we do thermal treatment to remove some water because I think Professor Tall also talked about ammonia will interact with water to get ammonia on. So we will remove the water by heating up like 20 degrees C. We found out the structure does not change much. No, so we do the isotherm, ammonia isotherm at room temperature. So we found out we can get this isotherm repeated for like at least 3 times. So that means we really did not lose any ammonia from the first cycle and second cycle. So that indicates us all this ammonia capture is reversible. So it's either weak physics option, weak chemistry option, or pure physics option. But here we have a huge jump at the beginning. So it probably indicates it's some strong absorption happening, but it's not strong enough to be stay there. Now, here we also going further. We did some in situ drift study. So after we got the MOF, we introduced nitrogen. We introduced ammonia. So we can see this, all this is OH stretching from this 3650. OH stretching disappears. So that indicates is some chemical interaction happens. If it's a physics option, it will not disappear, it just shift. So here I think it's OH interacting with the ammonia to get this NH4 plus. So this proton just transferred to the ammonia. And after that, we introduce argon. We see this OH peak generated again. Now, so it's basically telling us this is the reversible process. So it's this OH, this process is just going to right to the left. Now here indicates this proton is generates this NH4 plus. Now we want to know whether the rest two type of proton do the same thing. So we did this using this MOF, and we did this exosomes. Now we found out our expectation is we get higher uptake and reversible. Now here we found out it does not increase this uptake, and also it's not reversible. We lost some parts in the second cycle. Right, so it's very different from what we expected. You know, life is not always not that easy. Now here we call this is irreversible uptake, and this is reversible uptake. We're curious about what happens during this. So we also did the drifts, FTR. So it can tell us some chemistry happening in the MOF. Now, what we found out is when we heat up, the temperature increase, and this water peak disappears. So this water is, we go back, it's here, is terminal water quantitated with the zirconium. So this lost. So we found out this lost, making the less uptake, and probably maybe is this causing this irreversible uptake. Now we also do the similar thing. Okay, so here we lost this water and we generate this open metal size. So we hypothesis is this might leading to this irreversible uptake. So here we also did this drifts as the same procedure. We did ammonia and we did a natural argon protein to get rid of the physics of the ammonia. And we do see some peak here. This indicates this strong chem absorption because here the physics option all removed and the chem absorption of ammonia are left over. Now this comes from the NH bond from the coordination, ammonia coordinated under the zirconia open metal sites. Now here is the ammonia interacts with NUSRs and had two types of open metal sites can interact with ammonia by this coordination, and this proton can donate to ammonia to get this H4 plus. But this is reversible and this is irreversible because this is relatively weak, this is relatively strong. Now here is a quick summary. Is the prostate acidic sites in the MOF usually generate like a reversible uptake, so they can be used storage. And irreversible uptake is usually come from these loose acidic sites or open metal sites. So now we think about how to make it, more prostate acidic sites. And how to increase this reversible uptake and how to introduce more loose acidic sites to further increase the irreversible uptake. Now here is we introduce HCl. So because we think HCl, this proton is pretty strong as acidic. So we can introduce HCl on top of this MOF and we got totally 20 acidic protons. We think this might increase this reversible uptake. At the same time, we keep heating the node and we lose all this terminal or around ligands. And we hope this each zirconia can connect it to open metal sites. So they have totally 8 open metal sites. We want to test this hypothesis. Now here is how we make this chloride version. We're just using this formula version and we exchange this weak acid by using this strong acid, HCl. So now we got this in southern chloride. Here is a single crystal. We confirm the structure. Now the chloride really is a second sphere ions surrounding around this zirconia node. Then we did this exosome. We found out we do not we do not increase the reversible uptake, but irreversible uptake increased a lot compared to 2.5 and 4. So now, because here it also has water, we thought it might be the similar issues. No, we did the same thing. We did the ammonia purging, and then we heat up. So we found out the both qualitative ammonia, and we got this ammonia ions. So previously we didn't see this ammonia ions because ammonia ions is reversible in previous study. Now here, after argon purge, the ammonia ion is still there. That indicates it's irreversible. So basically, its hypothesis is like this: this proton connected with chloride is very acidic. So this acidic protons can interact with ammonia to get ammonia ion, but somehow this is very strong. It cannot remove back to ammonia. And here also coordinated ammonia there. Now, in terms of the Lewis acid sites, we got this. We use drift to confirm we remove all the OH and all the surface water ligands. And here we did this. We got the irreversible uptake, but clearly it does not increase much. It indicates each zirconium cannot coordinate with 2 ammonia, maybe 2 chloride on the zirconium. Now, one interesting thing we found out is when we introduced ammonia, we purged out the phases out, we left the chemsorption ammonia there. We found out the coordinated ammonia. It's not surprise because it's as we expected. We have zirconia open metal sites. And one thing we found out is zirconium, this NH2 stretching here. It indicates this is splitting happens, NH3 to NH2. At the same time, we find a very strong OHP coming up. So that indicates this process happening. Ammonia dissociate, go to NH2, and the proton go to the bridging oxygen to get OH stretching. Now, we cannot experience this using any experimental, so we rely on the experimental study. We found out what happened is there's some rotation happens. The bridging oxygen rotate to the end and generate this oxygen vacancy, kind of this oxygen going to the right. And here, if we put the first ammonia go inside, it will coordinate on open metal sites, and also it can split to NH2 and proton go to this oxygen. So now here, this is the preferred because it has a lower bonding free energy. Now, if you think about this, so here this rotation really generates this 4 zirconium with certain distance with this oxygen. So this distance is long enough to prevent to have a zirconium oxygen bond, but it's short enough it can coordinate some other gas. So here we'll continue doing this using restructured node due to CO2 capture or some other studies in my lab at RIT. All right, so I think it's time, but I will do a quick conclusion. So ammonia is very rich chemistry because it can be, so if we want to remove or separate ammonia, we want this irreversible bonding. So we want chemsorption, so at very low concentration, we get high uptake. If we want to do the storage, we want to store and release, probably we want to do the reversible uptake. We want to use this prostate acidic sites, but not strong acid, otherwise it will generate irreversible ammonia ions. For the conversion, this is what we continue doing here at IT, how to use this splitting. Usually ammonia decomposition starts from the ammonia splitting. So we want to see whether we can use this NH2 to get some amine containing compounds. All right, thank you. I'm ready for questions.
I'll bring mic to whoever wants to ask a question if there are any. If not, then I have, of course, 1 or 2. But one of them would be very easy. What I was thinking, this is also right now not in water, like this in pure air, right? So I think for calculation, it gets very convenient for to say. But what happens when you want to try to the scale or when you are trying to do selectivity? Because that's one thing for MOF. Everyone wants to know how good or how selective it is. So do you have you explored all those session side of it, or if so, is it something?
I think it's a very good question. So especially this water center, right? So how to water ammonia compete to bond because oxygen will bond. Usually oxygen bonds stronger compared to nitrogen. It's the same issue with CO2, right? Capture CO2 in presence of water. But when I listened to the talk from Tao, I thought about this. Maybe we can explore ammonia capture in the presence of water. I didn't do that before, but it's a good topic. Yeah.
Thank you so much. That puts in a lot of room. Any other questions? Anybody had any questions? If not, then let's move on to our next, our very own Clarkson speaker, Professor Andrescu. She's going to talk about something else, not nitrogen, for phosphorus, and the technology that she has developed over time. So I'll give it away to Professor Andrescu.
All right, thank you for inviting me to be here today. It's great to be here. So I will take a decidedly less technical view of things and take you more out into our farm fields where these sorbents and filters will actually be implemented. So I am from the Minor Institute in Shazy, New York. So you can see just a little bit cut off, but right up there in the far northeast corner of the state, so just south of Canada and right along the border of Lake Champlain. So we are a research and education facility. This includes a working dairy farm where we have 500 milking cows, as well as 1,300 acres of cropland that we manage in perennial alfalfa grass and corn rotation. So you can see us here along the Lake Champlain River. So Minor Institute is that northern star. And then some of the data I'll be sharing later on is from a collaborating farm that is a bit further south of us, about a half hour south of us. So I won't spend too much time on this because I could spend about the next hour just on this slide, but there's many reasons to install tile drainage. Certainly from a production standpoint, a lot of research that demonstrates the great benefits in crop production when we install tile drains. But there's also a lot of potential conservation benefits that we can see by lowering that water table early and then again late in the growing season. Allows us more time to do things such as plant cover crops, allows us more flexibility when we're managing our manure. And so all in all, while there are some risks, which we'll get into with tile drainage, there are certainly a lot of production benefits and potentially some environmental sustainability benefits as well. So just go back here real quick, just to make sure we're all on the same page here when we're talking about tile drainage. We're looking about 1 meter down in the soil surface, so about 3 to 4 feet. And then our laterals are spaced anywhere between 6 to 15 meters or 20 to 50 feet roughly. And so that's just, again, taking that water that might be ponding up in the field and dropping down that water table below the root zone. And so these are a couple maps of the Lake Champlain watershed where we're located. Again, here you can see these 2 yellow arrows pointing to our research locations. But so here on the right, we'll start with the areas in light green are our areas of agricultural land use. But then if we overlay this with this soil map here on the left, these yellow and red areas are marine and lacustrine clay soils. So as a result of our glacial history, We have a lot of very poorly drained clay soils along the coast of Lake Champlain. So you can essentially see where these yellow and red areas are. That's where the Lake Champlain or the Champlain Sea extent used to reach. Now Lake Champlain is much more narrow, but we're left with these lake and sea bottom soils, which create a lot of challenges. Now you can see, obviously, it's not a mistake or a coincidence, I should say, that our agricultural lands overlaid these poorly drained soils. In many cases, our more poorly drained soils are going to be more productive. That's what we see in the Midwest. Much of our agricultural land now used to be wetlands. Of course, we're not draining wetlands anymore for agriculture, but these poorly drained areas increase, or we see a lot of organic matter, typically more clay soils, which create more nutrient absorption capacity. It's definitely not unusual to see these poorly drained soils within our agricultural fields. So when it comes to dairy in particular, which is the sector of agriculture I work in, we're very lucky in many ways that we have a constant source of manure nutrients. Not only are we getting those, the NPK, the nutrients that we need, but we're getting a lot of beneficial aspects, the organic matter, the biological activity that's within that manure. But of course, with that manure source, with that fertility source, we have to figure out how to manage it properly. So when we're talking about agricultural nutrients in the Lake Champlain watershed and in a lot of New York State, we're going to be focused on phosphorus as our limiting nutrient in freshwater systems. So a lot of what makes this such a challenging issue is that the concentration in our lakes is very low, right? Phosphorus is the limiting nutrient, so any addition of phosphorus, even small additions, can potentially have a great impact. The good news for us is that phosphorus is relatively immobile in the soil. When we apply phosphorus fertilizer, it does relatively quickly and easily bind to the soil if that soil has not been yet oversaturated with phosphorus, which we'll get to. But so as a result of that binding capacity, oftentimes our phosphorus losses tend to be incidental losses, or those associated with manure applications and weather events. Or potentially we can also see soil erosion and that phosphorus that is bound to those soil particles being lost, and phosphorus losses occurring through that route as well. But because we do build up that phosphorus, or because we do bind that phosphorus to the soil, this allows the possibility for building up that those phosphorus levels in soils. So, 50, 70 years ago, this isn't something we were concerned about. And so there was sort of, insurance applications. Well, let's just get a little bit of extra phosphorus fertilizer on there. The soil is going to hold on to it. No reason to be concerned. Now later on, we're recognizing and having to deal with the legacy of those decisions. In saltwater, we're looking at nitrogen. Nitrogen acts very different than phosphorus, being very mobile, and much of our losses occur through leaching to either tile drains or to the groundwater. When we have saturated soils, generally we're going to see more denitrification, resulting in nitrous oxide emissions. When we have better drained soils, that's when we tend to see more leaching, because there's more opportunity for mineralization and transport. So because it doesn't readily accumulate as phosphorus does, we tend to see a bit different dynamics in our losses, and a lot more opportunity for loss as well, depending on how we're managing that manure and how the weather is interacting with that. But so what we really sort of struggle with is that when we're identifying practices that we're trying to maximize our drainage to get that water infiltrated into the soil profile so we don't have surface runoff and erosion. or limiting phosphorus, limiting nitrogen losses. All of these different practices that might target one of these often is going to result in a trade-off for the other. So when we talk about reducing phosphorus losses, we want to reduce erosion so we can increase drainage. What happens when we increase drainage? We increase our nitrate leaching. But if we want to reduce that phosphorus potential, or reduce that nitrogen loss, we reduce our drainage a bit, then we're seeing potentially more phosphorus erosion, potentially more greenhouse gas emissions. So it's really trying to understand how each of these practices impacts each of these factors, and then which practices are going to be able to sort of complement each other so that we can maximize all of them at the same time. I won't spend too much time on this, as I covered it a bit in the previous, and we'll talk about it a bit more. But you can see our general pathways over and through the soil. In general, there's really nothing we can say definitively as far as what impact does tile drainage have on water quality, because there's so many interrelated factors. What we can say with some certainty is that we generally see lower concentrations of phosphorus, both soluble as well as total, in surface runoff than in our tile drainage. But at the same time, we get higher flow volumes. So then the question is, while the concentrations might be lower, is that loading ultimately greater, the same, or less? And then another challenge is that clay soils do have the ability to transport that colloidal material in tile flows, and so we can see some sediment transport when we have heavier clay soils making it through to those tile drains. And again, where we have those colloidal particles, we could have phosphorus attached to it. But generally speaking, the amount of phosphorus we're exporting from our soils is very low. We're losing, this is the total P export from tiles. You see listed about 0.35 to 1.4 pounds per acre. That's from a review in 2015 of the tile drainage literature. We'll see later on with the data that I have to present, it falls pretty well within that range. But when we look at that range of less than a half a pound to about 1.5 pounds, that's maybe 1%. 2%. It's a very small percentage of what we're actually applying to that field. Some of the phosphorus that we apply to the field will remain plant available. Others will be adsorbed onto those soil particles, and then ultimately incorporated in, so that when we look at a soil test, we're not actually measuring how much phosphorus is in the soil, because there's much, much more phosphorus in the soil than what we could ever utilize. So when we look at our soil test results, what do we look at here? Here's an example. We have potentially plant available P, or Olsen P, milligrams per kilogram here in the bottom. That's actually really only going to be 1 to 2% of the total P that's in the soil, because it is so well bound. And then again, here you can see bottom right, an example. We've got a surface runoff sample full of sediment that was eroded, and a tile sample which is very clear, so not a lot of sediment, but of course, an unknown level of dissolved nutrients within it. But so there are some risk factors that we're aware of. One is, when did we apply manure relative to that runoff event? And so here we can see the fraction of runoff dissolved P that we would lose depending on the amount of days after application. This is from some work from Wisconsin by Vadas et al. But so what we see is, if we get that runoff event, if we get that precipitation sort of here, day 0, day 1, we run the risk of losing 80 to 100% of what we lose. But as soon as we start to get a week out, approximately a week out, we're well below 50%. And so this is one of the things our farms do. We have to look at the weather forecast the day, 2 days before to 2 days after every manure application in order to make sure that there aren't any runoff events. But of course, things do happen. The weather forecasts can be wrong. And so this is an example of a situation where we might see elevated losses. Again, this is an example of what happens when we have legacy phosphorus levels. So as I said, this is phosphorus in the soil. And then we have the amount that might be released to drainage waters here on the y-axis. And so what we can see is as we go from 0 until we get to about 60, we're increasing our soil phosphorus, but we're not actually increasing what is released to the drainage water. And it's not really until we get to this 60 milligrams per kilogram, or approximately 3 times what we would recommend in an agronomic setting for the phosphorus to be. And so we can see the soil does have a natural ability to bind that phosphorus. And it's not until we've sort of really oversaturated that system that we start to see that release. But again, this is a situation that not all of our fields are in, but a result of past management. Certainly some of them are. Another risk factor that we see is preferential flow pathways, and this can really impact what type of water we are getting into our tiles. So right here on the left, we have sort of our matrix flow, or the sort of uniform soil profile. In contrast, here on the right side, we see what happens when we get some cracks forming in the soils. Probably most of you have walked through a field. I don't have that picture. Walked through a field and seen some of these cracks right underneath your feet. That's what happens when the soil starts to dry out. It shrink swell soils, the amount of clay, as clay soils get wet, they swell, and then as they dry down, they shrink, and that's where those cracks come from. We could also have those naturally formed earthworm burrows, root channels, but what we see here is that blue representing that sort of drainage water wetting front. When we just have matrix flow or none of those large macropores, we're moving in sort of a slow, uniform front. In comparison, when we have these large cracks in the soil, the water can move very rapidly. So where we might have matrix flow occurring on the order of hours, preferential flow can essentially move on the order of seconds. And so generally speaking, preferential flow pathways are great for our fields with regards to drainage, right? The larger cracks means our fields are going to drain more rapidly, less surface runoff, less risk of erosion. But where we do have a risk is if these cracks end at a tile line, and we've had sort of direct connection from that surface water, from the surface, with that surface water moving down to the tiles. And so with that direct flow, that rapid flow, we are bypassing the ability of our soils to filter that. And so we can see here surface runoff, right? We see a considerable amount of erosion because we have no cover crop here shortly after the crop was harvested. And so we can imagine if that water is making its way through large cracks to the tile lines, that's going to be a lot different than what we might see if we have some more clear water with only dissolved nutrients to manage. There we go. Oops. All right, and so this is a couple hydrographs from 2 of our research fields that sort of demonstrate this connection of the drainage water from the surface to the tiles. So we can see the flow in liters per second from these 2 fields. These 2 fields are both about 5-acre fields, so it's not scaled by area, but roughly 5-acre fields. So we have flow in liters per second over the course of a 3-day drainage event. But so in gray here, we can see our precipitation spiking. Precipitation over on the right, we get right about a quarter of an inch very rapidly, and where we would expect if this was moving through the soil profile as matrix flow, we wouldn't expect to see sort of that concomitant increase in the tile flows until several hours later. But we see that tile flow peak at almost the exact same time as our precipitation is peaking, meaning there is that direct connection. That drainage at the surface is moving very rapidly down to our tiles. And so in these two fields with heavier clay content, we can see that rather than having that slightly more muted peak as the water was forced to diffuse through the soil profile, we can see that more sharp and rapid peak that coincides with our precipitation. But that doesn't have to be the case, and here I'll show in the next couple slides some data from one of our projects where we had two tile-drained plots and two undrained plots. And so what we see is here we have water yields. There we go, water yields on our vertical, a few days of a snowmelt and rainfall event in the winter. So we have the tile flow volume and the surface drainage from those tiled plots. And then we have the surface runoff only from those untiled plots. But so what we can see here is much more drainage occurring from those tiled plots, but all primarily occurring as tile flow, only a small amount of surface runoff. But then as we look at now total phosphorus, instead, what we see is that surface drainage line, which had much less drainage water. Now we look at the total phosphorus load, and we see that surface runoff was capable, or was delivering a lot more phosphorus than our tile drainage water was. So here we see our tile drainage water, much lower loading of phosphorus, indicating that as that drainage water moved through the soil profile, we were seeing phosphorus that started out in that surface water being removed by the tiles. And so we did see 2/3 more water, but half as much phosphorus. And so while we do have to be cognizant of the risk of preferential flow pathways, we also need to be cognizant of the fact that the soil can, in certain circumstances, be working for us as well. There we go. So a few more slides here. We'll look at some tile drainage overall. Here you can see one of our tile drainage monitoring locations. A tile outlet with flow monitoring device. And so we are sampling flow. We're monitoring flow every 15 minutes and then collecting samples as flow. One more slide. So, well, here we can see, so flow in liters per second, two of those fields again. But what we can see is here's a spring melt event that, generally speaking, the water that we have to manage is very episodic. So we can jump up to 2, 4, 6, 7 liters per second. But generally, those peak flows are only going to be occurring on the order of hours, several hours, maybe half a day, and then we drop back down closer to base flow levels. And then as we look at our concentrations, there we go. We have, so over the course of almost 10 years, about 1,500 tile or 1,400 tile drainage samples. But what we can see here is, generally speaking, the concentrations are very low and much lower than what is in surface runoff. So we see some peaks in our tile flow here, soluble on the right, total P, where we are getting up into the 1 milligram per liter range. But generally speaking, we are very low. And so again, it's these very seldomly seen concentration peaks that coincide with our flow peaks. And so it really could only be 1, 2, 3 events a year where we are seeing considerable phosphorus transport. But again, I didn't get to the slide here, but what our data has shown is that it's generally about, across the 10 years, we've monitored six fields. Only about 1.5% of the phosphorus we've applied as manure or commercial fertilizer has been lost in drainage. So again, that's reflective of the challenge of working with our drainage entering into a lake where phosphorus is that limiting nutrient, and even small impacts from agriculture where we may be retaining 98-99% of that phosphorus, but that small 0.5 pound, 1 pound per acre contribution can still have a significant impact on our water resources.
Thank you. Thank you so much for such an interesting talk. I know it gets very interesting. The more you talk about field, the more it's like, really what happens out in the field. It's definitely way beyond me, computational person, but I see where it goes. So it's very exciting. I know in the interest of time, we can have one quick question, or we can have Laura probably sit for lunch with us, and we can have questions if that's what panel wants. That's when we can probably do that way. So in the interest of time, I will thank all of the speakers, and I would like an opportunity to invite all the speakers to the stage so that we can have a group photo. And with this interesting, I'd like to thank also the Healthy Water Solutions to give us a chance to come up on the stage, give us talks, share the interesting